Hello, this is Pat Hindle, editor at Microwave Journal. It is my pleasure to welcome you to today's webinar on 4G and 5G wireless radio examples using the Zynq UltraScale RFSoC, presented by David Brubaker, Senior Product Line Manager at Xilinx. Before we begin the presentation, let me cover a few items about the On24 webinar platform. In the center of your screen, you will see a window containing the presentation. You may enlarge this to full screen to have a better view of the slides. The window on your screen labeled Resource List contains a copy of the presentation, which you can download at any time. This webinar is being recorded and will be available for replay so they can watch it again and recommend it to colleagues who weren't able to join us for the live event. You will find a link to the recording in the events section of the Microwave Journal website. If you have technical problems, please click on the yellow box with the question mark at the bottom of your screen. It will take you to a helpful user's guide. If you'd like to ask a question, just type it into the Q&A box on your screen and we will address it at the end of the event. In this webinar, Xilinx will provide an overview of two example radio designs for wireless communications that leverage the benefits of the Zynq UltraScale RFSoC. First, there will be a 64 by 64 massive MIMO 100 megahertz wide LTE example design with ORAN 7.2 split, which will be reviewed along with the implementation details and select performance data. And second, a mmWave transceiver design architecture that leverages the wide internal bandwidth of the RFSoC will be presented. Now I'd like to introduce today's presenter. David Brubaker is the Product Line Manager for the Zynq UltraScale RFSoC, where he's responsible for managing the early phase of the products, including the new product introduction and customer engagements. David has held leadership, technical, and marketing roles in several large companies, focusing on 3G, 4G, and 5G wireless infrastructure, including FPGA, ASIC, and ASSP solutions. He is a member of the IEEE and has a master's degree in electrical engineering from Santa Clara University and a bachelor's degree in physics from San Diego State University. So at this point, I will hand the presentation over to David.
Okay, thanks, Pat, and I want to thank everybody for joining the webinar. As mentioned, we're going to talk about some 4G and 5G examples that can be implemented on the Zynq UltraScale RFSoC. So let's go ahead and move ahead and take a look at the agenda for today. The first thing we want to do is give a brief overview on the ZU RFSoC and our roadmap and product families. This really ensures that everyone has a basic understanding of the ZU RFSoC on product specifications. And if you need more information on that, you can actually download much more detailed information at xilinx.com/RFSoC. After that, I'm going to take a brief look at the evolution of the radio network, primarily driven by 5G, and how some of Xilinx solutions can be used across the network. And then after that, we're going to kind of dig into the main part of the presentation, which is we're going to show a proof of concept massive MIMO radio developed at Xilinx. It's for sub-6 gigahertz, and it uses the ORAN 7.2 split. We're going to review the architecture and show some measured results, both conducted and radiated. And then finally, we're going to take a really quick look at some mmWave beamforming architectures using the ZU RFSoC, but I primarily want to show the benefit of using that device as an IF transceiver due to its high sample rate and wide bandwidth. Okay, so we're going to move on. So the next one, we'll go ahead and talk a little bit about the roadmap here. So this is an outline, kind of what we call a round-the-world drawing of our FPGAs. And if you're actually familiar with the Zynq UltraScale MPSoC family, then you'll be familiar with the Zynq UltraScale RFSoC family, because actually the RFSoC is based on the MPSoC family, and it leverages the same quad-core ARM A53s, the dual R5s, all the platform management units, and the hard IP, the transceivers are all the same as in the Zynq UltraScale MPSoC family. The only difference is we add two key IPs, hardened IPs. First is the direct sampling ADCs and DACs shown at the bottom. and then the soft decision forward error correction. Now, I'm not going to do much detail on the SD-FEC, as we call it here, but it does support LDPC and turbo for both 4G and 5G applications. Now, the other thing I want to mention is that we do, in the 16 nanometer programmable logic device, just like the MPSoC, but we also have a lot of DSPs in this particular device. It's DSP rich with 4,272 DSP slices. Now, I want to take a moment and kind of describe how the ADCs and the DACs are implemented. You can see them on the bottom of the die here, and in reality, they're implemented as tiles. Each tile contains either 4 ADCs or 4 DACs. And so we have 4 tiles of ADCs and 4 tiles of DACs. That gives us a maximum of 16 ADCs and 16 DACs. That's the maximum configuration of RF sampling converters. So we can actually then configure them in different types of modes to provide different kind of performance. And one of the things we do for the ADCs, instead of actually having always 16 ADCs, we can implement an 8 ADC solution and time interleave 2 of those ADCs to provide essentially twice the sample rate. Okay, so let's go ahead and take a look at the roadmap to talk about what we're doing in the future and what we're doing today. So roughly in about 2017, we announced the ZU RFSoC, and I'm going to refer to it frequently as ZU just to abbreviate the Zynq UltraScale Plus. We announced it in 2017, and it went to full production in 2018. That's called our Gen 1 device. It's where it says breakthrough integration. And the input and output bandwidth of the ADCs and DACs go from DC to 4 gigahertz, and that's what we say is the 4 gigahertz analog bandwidth. Now, it's available in either an 8x8 or 16x16 ADC and DAC configuration. When it's in the 16 ADC configuration, we roughly sample it around 2 gigasample. When we have it in the 8 ADC configuration, it's roughly around 4 gigasample, as shown there. In this Gen 1 device, the DAC is always sampling at about 6.55 gigasamples per second. Now, even though the analog bandwidth of the input and output go to 4 gigahertz, your actual instantaneous bandwidth is always limited by the Nyquist bandwidth. But we can actually sample in the 2nd and 3rd Nyquist zones, so you can actually have performance up to 4 gigahertz. Now, in 2018, we announced, and in June of this year, in 2019, we announced the Gen 2 device. Now, Gen 2 is primarily a frequency shift of the input and output matching network to 5 gigahertz, and it's only available in a 16 by 16 configuration, as shown here. It's primarily aimed at the 5G new radio markets in Japan and Asia to be in full production by 2020. So that part is also in production. It's called Gen 2. Now, our Gen 3 device, we announced it in 2019, and in this particular case, we added a lot more features to this device. We have quite a new improvements in the hard IP block, but primarily we upped the input-output bandwidth to 6 gigahertz. That allows us to cover all the sub-6 gigahertz bands. We also increased the ADC sample rate by about 25%. So, for example, in the 16 by configuration, we can sample up to 2.5 gigasample, and in the 8 by configuration, up to 5 gigasample. The DAC sample rate is also now increased to 10 gigasample. So that part is actually back, and we did some demos at our Xilinx Developer Forum in Europe and in the United States recently, and it will be sampling in Q1 of 2020. And it'll go to full production in Q3 of 2020. Now, the other thing I want to mention is that basically about a year ago at the Xilinx Developer Forum, it was almost a year ago, Xilinx announced their 7 nanometer device. That's called the Versal platform. And in that platform, we announced several series, one of which was called the AI RF. And that is a 7 nanometer part with monolithic direct sampling ADCs on it also. Now, the AI moniker actually means Adaptable Intelligent Engine. And so that particular device has what we call a vector processor, and it's arranged in a 2-dimensional array to really benefit DFE type processing and matrix type calculations. That part is also back in sampling, and for not the AI RF series, but the other series we have available. And you can actually get more information on that also at Xilinx.com. Okay, so I'm going to actually show the full product family here. And I'm not going to go over this in detail because all of it's actually on the web, but I do want to point out several key parts. This product summary actually includes Gen 1, Gen 2, and Gen 3, so you can see all the parts that are available. And we kind of have a matrix of the different parts and performance. Primarily, each part is a different mix of either ADCs and DACs or SD FET blocks. And I do want to point out in particular a couple things. We have on the far left a ZU21DR. That's a part that doesn't have any ADCs and DACs, but it has the SD FETs. It's currently used in several baseband applications in the wireless system because it supports, as I've already mentioned, LDPC for 5G new radio and turbo. The other thing is, if you take an analogous part in, say, the Gen 1 or Gen 2 or Gen 3, the packages are forward compatible. And the way, excuse me, I have a little bit of a cold here, so my voice is going to break up a couple times through the presentation. But if you look at an analogous part, like, for example, the ZU27 and the ZU47, they're forward package compatible. In other words, the pinouts are in the same location, so you can migrate between families with package compatibility. And that's another benefit. Okay, so let's take a look at the radio network evolution and talk a little bit about that because it kind of derives the reason for what we're doing. And here we're kind of showing the basic network evolution. And I think the key point that I want to point out here is the breakup between, the traditional BBU unit to essentially a central unit, which has non-real-time baseband function, and a distributed unit that has real-time baseband. And they're shown there. That would actually be connected back, to the mobile core somehow. Now, what's actually interesting about this is that if you look going forward in 5G, there's a lot of press about massive MIMO, and of course we're going to talk about that today, and mmWave, and I'm going to talk about that today also a little bit. But there's also going to be a lot of macros used in the system. There's, strictly because not all of these solutions are ideal for every application, and we'll talk about, some of the areas where they're more useful. Now, one of the things I haven't shown in this slide is the coexistence of 4G and earlier networks that will have to be supported in parallel as the operators roll out 5G. This is a topic what we call converged access, and it's really too large for today's discussion. However, we have done a lot of work on it, and if you search, quote, Xilinx converged access, close quote, you can see some of the work we're doing on the converged access in this area. And then lastly, I really need to mention that we have, starting really with 4G, the migration to a virtual BBU. And then this is a case where we use CPUs to do many of the functions previously done by, say, purpose-built ASICs or ASSPs. This actually, as I mentioned, started with 4G, but it also is continuing on with 5G. And there's several benefits of that, because of the ability to repurpose the hardware, the functions that are being done on the BBU. But one of the things is that if you take a look at that virtual BBU, it really needs some kind of L1 acceleration to improve the efficiency. And a simple one-card hardware accelerator with one FPGA can actually replace several CPUs and hence improving the CPU efficiency. Now, typically, the hardware accelerator is done in a PCI card like the one I'm showing here. This is a card that's available from Xilinx. It's a full-height, half-length PCI card, and we do connect to that with the PCI Gen 3. But because we actually have the L1 LDPC and turbo codes hardened into the ZU21, you can see the ZU21 is on that. It can support turbo and LDPC codes. And in this case, we actually do the polar codes in soft logic. It also does the front haul termination with 25 gig eCPRI, and we support the RF spec and the 1588 with that, and also support any of the aggregation logic and packet classification. So this is a card that's available from Xilinx for acceleration of the virtual DU. Okay. So next, we're going to move on to our ORU massive MIMO example. But before we get to that, I want to spend a little time and talk about why massive MIMO is important. As the user data rate consumption rises, and we've all seen the exponential growth charts with data rate usage by users, the operators face a challenge. And the challenge is how to get more bandwidth to the user and even to more users. Okay, so traditional methods, if you just densify the network like I'm showing here in the upper part by adding more base stations, actually can lead to higher interference. And the other point that's not always mentioned is that it's actually quite expensive to add additional base stations, particularly in urban environments where you've got to run the backhaul network and then get site acquisition costs. So it's actually not always the best way to improve capacity. Massive MIMO, on the other hand, is kind of scalable in the sense that because you can take advantage of multi-user MIMO and beamforming techniques to mitigate interference, you can get 3x or more gains in capacity just simply by implementing a massive MIMO network. And these gains are done primarily on the existing sites by basically replacing traditional macro antennas with massive MIMO heads. And hence, it's actually got lower build-out costs. So this is an area where we're seeing a lot of growth in massive MIMO. It actually started with LTE, but it'll continue on with 5G. Now, this technology, particularly because of the multi-user MIMO and the multipath that we want to take advantage of, is usually best in urban environments and sub-6 gigahertz bands. But that's actually where you need the most capacity growth, is in a dense urban environment. So it's well suited for that. And the other thing I want to point out is if you actually do massive MIMO, because of the interference mitigation, you actually get a higher QoS, as shown in the lower figure, for all the users. So you don't have the edge, the cell edge interference issues that you would have with the architecture above. Okay, so now let's take a look at the ORAN functional partition, and this is basically a way we break up the entire process of going from essentially ultimately the mobile core all the way to the radio and back. And so it's showing here the various functional splits that exist going through all the steps that you would go from the say the MAC and the downlink all the way to the radio. Now, in the traditional format, in 3G and 4G, they would be implemented in what we call the split 8, as shown in the lower right part in red, and that would be the typical CIPRI split, okay? Now, there's actually numerous splits defined. There's, as I've shown here, a 7.1, a 7.2, and typically, for ORAN, they've adopted a 7.2x, as we say, okay? And the reason this is happening is that if you take a look at the capacity required by 64T, 64R, a 100 megahertz system, at each point in these splits, you can see that as you go to the traditional split 8, that particular system would require 236 gigabits per second. It's just not possible to run that kind of data rate to a radio head. So essentially, by moving back in these splits, we can decrease the bandwidth. And if you look at the 7.2 split, that same radio is a manageable 20 gigabits per second, okay? So that's typically where a lot of people are landing on the split. And what that does is it moves processing that used to be in the BBU or, let's say the DU up into the radio unit. For example, the beamforming, in particular, if you look at the legacy systems to 4G, is the IFT, and the FFT are now up in the radio unit. Now, the other thing I want to point out is that these are just nominal splits recommended by ORAN. There can be other splits and other things that get implemented. So operators actually have to be able to handle multiple kind of splits with different kinds of data and so forth. And that type of an application is really well suited to an FPGA where you can change the split or some of the the configurations that were required between, say, different DUs and different radio units. Okay, now we want to move on, and I want to take a quick look at, let's take a look at an example ORU radio. So we're going to talk about an ORU radio, and this would be a device that has the 7.2 split. We would actually come in at, on some sort of an N by 25 gig E-link, and then you would have the transceivers and so forth that would be required for that, the Ethernet. But then you would actually have the eCPRI layer and then the ORAN layer. And that would break off, in that system at the front-end unit. This is kind of what I call an aggregator unit. It has an embedded PS, so it can do some management and timing, synchronization plane. But you have the user plane and the control plane that then ultimately feed to a TX beamformer, and then to the in the downlink path, the FFT, and then ultimately you could go over to multiple cards, doing what we call the traditional DFE functions. That would be up conversion, filters, CFR, and DPD. And then on the downlink, you would have your ADC. It would go in typically through a DDC and some sort of a channel filter, again going through the transform back into the RX beamformer. So this is kind of a typical 7.2 split and how it could be architected. But there's actually many different ORU functional partitions and even implementations of this that can be done. Now, let's take a look at what we call our proof of concept. So what we did to do, the goal here is to develop a proof of concept ORAN functionality that's basically functional and mechanically similar to what a customer would implement. And that we wanted to do this, primarily to understand the issues with massive MIMO implementation using FPGAs and some of the IP that's required to make this system work. What we did is we implemented an LTE massive MIMO system using the ZU RFSoC, including the RF electronics, so we had separate RF cards, PAs, filters, and an antenna array. The target specifications we have, I've shown here, we're operating at band 40 or 41. The duplex mode in this case is TDD, and we have a maximum of 5 carriers. The occupied bandwidth is 100 megahertz as well as the maximum instantaneous bandwidth. So it's either 1 by 20 or 5 by 20 carriers. Typical power, about 80 watts is what we were looking at. So we did have a PA that's running at about 1.2 watts at the output. This design was to support 16 layers on the uplink and 8 layers on the downlink. And again, we mentioned Zynq and 1588 synchronization. Okay, now we have kind of a proposed mechanical concept here on the right. It's not really detailed. Well, I'll show you a couple more pictures here in a minute. But the idea is that you have a digital board on the bottom, and then you'll have an RF card that'll be stacked on top of that. And then you have an antenna panel, which actually implements the antennas. And this is all connected together so that we can make not only conducted measurements when we remove the panel, but also radiated measurements on the system. So this was our proof of concept target. And now I'm going to take a look at, actually how we implemented it, okay? So what we chose for what we would, I've mentioned is the aggregator FPGA, or the one that does the front haul termination. We chose the ZU21DR. And that actually does have the SDFX. They're not used in this case, but it can implement the Ethernet and the eCPRI and the ORAN front haul interface. And one of the reasons we chose this part is because it actually has quite a bit of URAM and DRAM memory, and that's used intensively with the ORAN interface. So it'll do the host and management, the drivers, and then we actually implement the uplink and downlink beamforming on this device. Then we would connect those to another card, and each one of these cards are identical, and they basically consist of a ZU29DR. Now that is an RFSoC that has 16 TX and 16 RX ports, so it can do a 16 by 16 array and then transmit anywhere between DC and 4 gigahertz as we set up the frequency plan. In this case, as I mentioned, we're looking at band 40 and 41 for this. Now, when you look at what's implemented on this card, it's always the same. It's the cyclic prefix and the FFT and the IFFTs. We do some PRATCH filtering, but then the traditional DFE functions, including the DUC, CFR, DPD, are all implemented on that particular card. And after that, each one of these cards interfaces to an identical 16-channel RF module, which actually takes the input, again, which is RF, but we have some additional functionality required at the RF. Let's take a look at that right now. So if we take a look at the next slide, okay, this is a block diagram of what we're doing on the RF card. So for example, here we're showing the DAC output and the ADC in. That would go right to the ZU29DR card. And there's actually 16 of these identical paths, okay? So we have some buffer amps, a little bit of filtering. We actually have DPD feedback, okay? So the DPD is implemented on the ZU29. And then we also have a circulator, okay? But we also, what's very important, have a calibration path, because any of these massive MIMO systems, you need to calibrate all the paths so that they're aligned. And we're going to take a look at the performance of that in a minute. Okay. So as I mentioned, the output power at the antenna port is about 1.2 watts for each antenna port. Now, it's interesting that what actually happens is, this is a picture of the RF module. So this has got 16 of those RF chains, each, for the 16 separate antennas. And so there would be 4 of these in the final array system, making up the 64 by 64 antenna. Okay, so I want to take a quick moment and show some, basically results and what we got in the device. So I've shown a couple cases. Now this is what we call the LTE 1 carrier 16 antenna, and then the LTE 3 carrier 16 antennas. And if you look at it, the ZU21 is pretty much the same, but the big item there that we're consuming is not so much logic in the ZU21 device board, but primarily the BRAM and the URAMs are quite high. Okay, and that's all, as I've mentioned, primarily implementing the ORAN requirements. Now, if you look at the ZU29, we're running reasonably low on the logic. It's a reasonable number. It's less than 50%. But the power of that entire system is actually in the low 40s to mid 40 watt power, as I've shown you right here. And I want to point that out because if you were to implement 40 watts a few years ago in any FPGA, you really couldn't cool it, particularly in a remote radio head environment. But we face a challenge with these massive MIMO systems. We have 64 parallel transmitters and receivers and DFEs, and all that requires power that and power density that really wasn't required in earlier systems. The reason that we can put up with that is because we have the added benefit of the capacity gain. So I want to point out what we're doing now to handle this kind of power dissipation, because a few years ago, you really couldn't dissipate that kind of power. So what I'm showing you here is a picture of what we call our lidless technology. It's a little bit covering the device, but or the words. So this lidless technology significantly improves the cooling versus a lidded package, and you can see a picture of it there, and you can see the monolithic die. So our RFSoC is a monolithic 16 nanometer die, and all the ADCs and DACs are all on one die. But on the outer edge is what we call a stiffener ring, so that stiffens the package, okay? And in this case, instead of actually contacting a lid, the heatsink directly contacts the silicon. So let's take a picture of that drawing. And what I've shown here on the left is what we call our traditional thermal design, and on the right, enhanced thermal design. So on the left, we actually have to go through, from the die to get the heat out, we have to go through typically a small thermal insulation, what we call TMI, thermal interface material, between the die and the lid. And then we have the lid, and then we have another TIM, which is between the lid and the heat sink, ultimately, okay? And then on the right, what we have is the same design, but we don't have a lid. So we only have one TIM, and it's basically connecting the heat sink right to the top of the die. So this is what we're doing, okay? And we did an experiment. We dissipated, up to 50 watts in those packages, and then measured, for a typical heat sink, what would be the improvement in performance. So if you look at traditional thermal design and we have ambient and 45, you can see the maximum junction in that case can actually reach 120 degrees C. And the maximum junction for most semiconductor FPGAs are 100. But by implementing this enhanced thermal technique, we can actually reduce that junction temperature to 92 degrees. So, the overall result is we see a 28-degree improvement from traditional, and you actually see an 8x reduction in theta JC according to the JEDEC spec. We go from 0.16 to 0.02 degrees C per watt. So that enables you to run more power and still meet the junction temperature. Okay, we actually have an app note on this. It's called 1301. You can go online and take a look at it. And all of our RFSoCs are available in both lidded and lidless, and many other of our Vertex families are available in lidless also. So the last thing I want to point out is that the RFSoC is actually available in what we call a -2Li speed grade, and that supports wireless frequency plans up to 110 degrees. So the key frequencies, 491.52, are all supported up to that frequency with that speed grade. But it has a little bit lower, the L is lower static power, I think. And so what we also do is we allow that device to operate up to 110, okay? And we guarantee all the timing up to 110 for that device. And we also guarantee a 10-year lifetime if the exposure between, say, 100 and 110 is less than 5% of lifetime. And that's actually typical if you look at like a normal daily and annual temperature extremes in any environment. It's not 100 degrees, or hot. It's only hot during the afternoon, and then you have the winter and summer. So typically this 5% rule is quite adequate. And so we've made this part available. And it also enables you to operate in these wireless systems that are mounted on a pole in direct sunlight. Okay, so I'm going to move on now and take a look at, let's take a look at kind of what we did in some of our conductive measurements. So what I'm showing you here is it's not exactly easy because I had to draw some stuff with some help. But this kind of shows kind of how we're making our conductive measurement, and you can see the beamformer and then the digital cards there. And I'm showing off to the right the RF module. In reality, they would be stacked above that, but I wanted to clear them off so you could see how that's actually connected. And then we would use some attenuators and various test equipments to actually make some conductive measurements. And so here's kind of a picture of exactly everything, but unfortunately we've got the kind of the combiner network on top of it. But you can see underneath that are the RF cards, and then there's the interface card that implements the 1588 there on the bottom. So this is kind of a radio compliance test when we set up to do some of the conductive measurements for the downlink. Okay, so let's move on and take a look at some of the data. Okay, so this is some example data we took of the ORU design operating, and you can see the TDD waveform there. It's it's a little bit hard to read, but you know how it is when you get the data right off the spectrum analyzer. And in this upper, let's break it into the left side and the right side, and we'll cover the right side in a minute because there's some key information there. But on the left side, you got multiple plots, right? So you see the TDD waveform, and you've got the EVM across the carrier. In the upper right, on that left plot, you can actually see the transmit waveform. It's not perfectly clear, but the ACLR is better than 50 to 55 dBc there, okay, and including DPD. And then in the box on the lower left, we have many parameters. And if you look at it, what's kind of interesting is that we see typically an EVM of about 1%. Okay, which is quite good in that case. But the IQ offset is actually very good at somewhere around 90 to 100 dB. And that's because that IQ separation is implemented digitally in the RFSoC. And on the right there, we see the constellation of a 256 QAM LTE signal. Now, let's move over to the figure on the right. Now, this is an interesting curve because what we're showing here now is based upon different antenna ports, what is the EVM as a function of QAM? Okay, so the black is 64 QAM and the red is 256 clam, but you can see that it varies quite a bit from channel to channel. Okay, somewhere from around 0.7% EVM all the way up to about 2%. And the reason for that is actually because the isolation between some of the channels varies. Okay, and this is something to be very mindful of whenever you're making a massive MIMO system. If you get any interference from the different channels, it can actually be kind of an interferer and then degrade your EVM. So that's what the difference is attributed to. Now, in this case, they're all lower than 2%. The system spec is about 3.5, so it's pretty good. But obviously, one needs to be very mindful of the isolation. And that's another reason we built this entire RF card, is to kind of learn these lessons that would be faced for anybody building this type of system. Okay, so another very important parameter of any massive MIMO system is calibration and how accurately you can control the gain and phase of all the channels. So after we built this entire system up with all of the digital electronics and all the RF electronics, we implemented our calibration routine, and here is the measured gain variation over time of all 16 channels there, and the phase difference. And so what we're seeing here on this measurement is less than 1 dB peak to peak in the gain difference over time, and then less than 5 degrees, or about 5 degrees peak to peak over time. Now, the reason we're looking at this over time is the cal routine actually runs continuously and kind of a round robin, and it basically updates each channel gets kind of re-updated about every 60 seconds. So it's important to look at the drift between calibration as it gets updated. And so you can see that the RFSoC and all the electronics is very stable once it's running, and the cal routine can provide pretty good calibration with that. I think it's actually very good data on that. And this, again, I want to mention, includes all the digital and all the RF electronics included. Okay, so next, let's take a look at some actual radiated measurements. I did say that we did do radiated measurements, so we put the antenna panel on and then measured in a anechoic chamber. And so on the left, we have kind of the equal weight beamform pattern. And what's there, it's a little hard to see, you know, if you get the presentation, you can look at it, is you can actually see the theory and measurement, and it's actually got quite good correlation between the theory and measurement of the antenna array. And, you know, there is degradation above 70 degrees on the angle, but that's primarily because of the degradation in the measurement setup. Okay, and then on the right, what I'm showing is, you know, what we could do by improving the side lobes. And so all we've done there is do amplitude weighting on the various antenna elements to get better than 20 dB side lobe performance. And that's shown there. So again, I think very good performance of the transmitter, including calibration using beamforming and all the analog and antenna panel. And it's measured in an anechoic chamber. Okay. Now, the next thing that's of interest in any sort of massive MIMO application is, you know, beam steering and, you know, what we would call beam shaping. Okay. So I'm showing that here. This particular case, we have on the left, we have beam steering. Okay. So you can actually see how we can steer the beam. Again, we have theory and measurement there, which is pretty good results and correlation. But we can see, typically, you know, you can steer the beam roughly about 45 degrees from the bore site with this particular antenna. Now on the right, what we're showing is the ability to do beam forming. And so we can actually narrow the beam to, say, plus or minus 10 degrees or less. You can see it as the light kind of blue teal line, but then you can also broaden the beam in the purple and the other lines. Again, this is done, I think this one is done with amplitude weighting too, but it allows you to say, you know, focus on one particular user or even hit a broader group of users by doing the beam shaping in that case. Okay. So that's the summary of the data I have on the millimeter wave, the sub-6 massive MIMO. And I'm going to move on now to the millimeter wave application. So if you take a look at the millimeter wave, now millimeter wave, as I mentioned, is getting quite a bit of press in the system these days. It has its challenges, but it has its advantages. One of the advantages is it's got tremendous amount of bandwidth, compared to what we have in the sub-6 and lower bands, so you can have a lot more capacity. But it has, a very short range. It's typically what we would call maybe a picocell, and can do some of the last mile type wireless distribution, or even, in like a stadium view. So there's a lot of work going on it. And if you look at the system here, the basic block diagram is somewhat similar to what we would do in the other device, where we would have some sort of an ORAN interface. In this case, on the left, that would really have to go into another FPGA to implement the full ORAN. But we would have the FFT, the IFFT. There's got to be some kind of channel equalization, and then there could be a digital beamformer. But in a lot of cases, most of this is what we would call analog beamforming. Okay, so there would be some sort of essentially beam steering, and there's a control mechanism that goes over to a millimeter wave beamformer shown in this millimeter wave module. And then from the millimeter wave modules that are on kind of the right, where we have an array of them, there's actually what we call a block up and down converter. Okay, so this is essentially an LO and mixer and filter, and then you block convert that bandwidth that's at millimeter wave, and typically that bandwidth is 400 megahertz minimum. It can be 800 megahertz, and so now at the somewhere in the IF range, I've got it shown here 4 to 6 gigahertz. You're going to have 400 megahertz or 800 megahertz that you actually need to sample and digitize for digital processing. Now, it turns out that the ZU47DR, because that particular part now goes to 4 to 6 gigahertz on the analog input, and we have a higher sample rate, you can actually implement quite inefficient, and I'm going to show that next, frequency plan to do an IF transceiver for millimeter wave. Now, we've actually demonstrated some millimeter wave radios with a couple companies. For example, at Mobile World Congress in Europe 2019, we did a demo with mmWave, okay? And you can look back and find the references on that. And then at Mobile World Congress Americas in 2019, that was just a few months ago, we did a demo with Movandi. So a lot of these particular companies will implement either the beamformer or the millimeter wave electronics and the head end, and then even the block converters. But we could interface with those to actually do the rest of the processing. So the last thing I actually want to show is a millimeter wave frequency plan. And I think this is important in kind of a tool that we have. If you go online, there's a link there, but it's essentially at Xilinx.com/RFSoC/documents. There's a documentation tab. You can find a frequency planning tool. And this tool actually helps you plan, what you can do with your frequency plan for both the TX and the RX. And I'm showing an example here. And in this case, what I'm doing is, if you look at the PLL reference clock, I picked a reference clock of 614.4. In general, the higher your reference frequency you can put in, the better your phase noise will be of any onboard, on-chip PLL that we have. But it also makes your spurious plan much simpler for very wideband IF. So that's why I picked it. Our signal bandwidth I'm showing here is 400 megahertz on the TX, but I'm also, and with that particular frequency plan, I picked a DAC sampling rate of 8601.6 megasamples per second. Okay, so that's the actual RF sampling clock. And in that case, you can pick a signal center, the IF, at 5100 megahertz, and that's shown with the blue curve, okay? And actually, I need to go forward on the slide here. On the left over here. So you can see that the blue curve here, we're showing the band of interest on the transmitter. Okay, so that would be the output, but it also shows you the spurs that are around the various harmonics. And if you look at this harmonic number over on the left, the higher the number, the lower the spur. And typically, if you're operating with a fourth harmonic or above, it's not anything to worry about. And you can see that we have quite a bit of room to implement that particular frequency plan at 5100. Now, on the right, what I'm showing is the receiver. And one of the reasons I picked this plan to show is that we can actually pick an RF sampling rate of 4300.8. Okay, so that's exactly half of the TX, so it can be implemented essentially as a divider. And then we can actually also use the exact same IF for the RX as we did for the TX. So in this case, you can see the band of interest. If you were to input that 5100, the band of interest is shown where it would be in the IF after down conversion, okay? And then you can see the various harmonics that would be in band or out of band. And again, this particular frequency plan is quite good for that. So the final thing I kind of want to mention here is that the ZU Plus RFSoC actually has RF sampling PLLs on board, so you can actually generate those by putting the reference signal in, or you can actually use external RF sampling clocks if you want better phase noise. And on this particular case, one of the advantages, if the TX and the IF are actually, TX and RX IF are actually at the same frequency, 5100, you can actually reuse the TX and the RX filters. You can either do those by putting two of them down or use a switch to switch between them in the filter. But it does simplify the design if you can put them at the same frequency and so forth. So moving on, then I guess what we want to do is basically kind of conclude this, because that's all the information I have, is we've talked a little bit about the evolution of the network and kind of why that's driving massive MIMO and mmWave a little bit, and the disaggregation of the baseband unit into the DU and the CU. If you look at going forward in 5G, sorry, you're going to see multiple radio type implementations. There's going to be macro, massive MIMO, even some small cells. There'll be sub-6 and mmWave instances, and they'll all use some kind of spatial beamforming or beam steering, particularly in the massive MIMO type applications. So we did implement a proof of concept in the band 40 and 41 using the RFSoC. It's basically a stack design, okay, kind of how we would view a customer to build that particular part, and we did implement it with an antenna panel. We feel the results are pretty good, the performance to what we would call our target requirements. And in particular, some of the things that we found to be very important is the isolation between all the antennas and the calibration routine to maintain stability between all the channels, all the beams. Lastly, I didn't do a lot of detail in the architecture because we were just going to run out of time, but the RFSoC Gen 3 is ideal for a mmWave IF transceiver. You can actually do up to 800 megahertz. I know I showed a 400 megahertz design, but that design is actually capable of 800 megahertz in the 4 to 6 range. If you actually need, a lower bandwidth, you can actually implement many different frequency plans depending on your needs. So that's all I have, and I'd like to open it up for any questions.
Thank you, David. Very informative presentation. So we do have time for questions. If you'd like to ask a question, just type it into the Q&A box on your screen, and we'll get to as many as we can. So the first question, in the frequency plan for mmWave, you show a reference for 614.4 megahertz. Can you use a 491.52 megahertz reference instead?
Yeah, that's a good question. I would say, if you were to start off on this, most people would use a 491.52 frequency because it's related, to the 122.88 and easily done. The reason I picked 614 is because it's actually a larger frequency and then keeps all the spurs further apart. But the 491.52 works. It can also do 400 megahertz. And I believe in that case you would pick, I think it's about, you can work it out, but the RFLO is roughly around 7.8 gigahertz or something like that for the sample clock. And in that case, what you would have to do is implement a slightly different IF, and in particular, a slightly different IF for the TX and the RX. They would be shifted a little bit, so you'd have a separate center frequency for the TX and RFIF to maintain your best spurious performance, but it can be done.
Great. Next question, do you have a product to use as a modem for wireless E-band backhaul?
Well, this part can certainly be used for that, and what we do is we have a partner that we work with to do the E-band backhaul, and I can reach out to that person directly and put you in contact with our partner. But yeah, the device has been used for E-band microwave modems.
Okay, next question on slide 15. I think you're talking about the power draw. How much power was that drawing? I think maybe 50 watts, you said?
It was in the low 40s to mid 40s.
Okay.
On what slide was it?
15.
15. Yeah, this one, and that's for the ZU29 card. The power, is it out there? Can you see the picture now?
Yes.
Yeah. Okay, so the power all depends on what you put in it, and you know everything you get into it, depending on how big your DPD is and your CFR. In our case, we were in the mid 40s for 3 carriers. Of course, that would go up for 5 carriers. You could actually implement less logic and reduce the power. But in our case, particularly since we have the lidless design technology, we can run these devices up into the certainly the mid 40s and even high 40 watts power, and still maintain adequate cooling for a remote radio head mounted on a pole, in the sun, in the desert. We've done that thermal analysis.
Next question, how is the ORAN front hall interface implemented? Does Xilinx provide a working IP core?
We have partners again on that. We've done parts of it, but we do have different partners. So I think it's best if I respond directly with the team that does that. It's a slightly different group than I work in, but I can connect them with that team that does the ORAN interface.
Okay, next question, do you handle FDD?
Okay, absolutely. Of course, I didn't mention it, but in the Gen 3 portfolio, we have a part called the ZU 4060R. It actually has 12 DACs and 12 ADCs. 8 of the ADCs are what we would call the half speed, or the non-interleaved, and then there's 4 that are interleaved for higher sample rate. That device is designed specifically for FDD, and it can implement an 8x8 system with the feedback or observation data converters, the receivers, on one chip. Okay, so we do support it. I think the difficulty with FDD is always going to be, how you do your channel estimation. And in our case, the TDD makes the channel estimation simpler for the massive MIMO case, but there are many algorithms and work on FDD systems for channel estimation. I'm not really on all those.
Okay. Next question, what software options are available to perform automated calibration in the transmit and receive paths? Well, as I mentioned, this was kind of done as a proof of concept learning experiment, and I'm presuming that question is related to the massive MIMO implementation. We don't really provide software for that, particularly in terms of an automated scheme. Our particular system is closed loop, and so it's running continuously, as I've mentioned. But it's not really set up to be, I think I'm reading it as an automated system that may be in a factory calibration, but it doesn't do that at all. It's set up to run continuously and then calibrate the channels on kind of a round robin
So kind of a background calibration for aligning the gain and phase of all the antenna paths.
And the next question, how do you distribute reference clocks?
Okay, so there's many options for that. Okay, so as I mentioned, each tile, there's four DAC tiles and 4 AD tiles for each part. You can actually input a reference clock to each of those and generate with an onboard PLL separately for each tile. Okay, you can input an RF sampling clock, and if you want to use your own generator, primarily to have higher phase, better phase noise, you could generate the direct RF sampling clock. That's the one at, say, 8 gigahertz or something like that, or 4 gigahertz. You can generate that yourself and then input it to any of the tiles. We also have some on-chip buffering and muxing capability so that you could input it in one port and then distribute it to the other tiles. So in short, there's a lot of options, too many to discuss. I think that's probably best handled separately by myself responding to the actual use case that the person wants. But suffice it to say, there's a lot of options that you can do on that.
Next question, is there a DUC or DDC IP from Xilinx for the bandwidth more than 20 megahertz?
I would be certain there is. I can't, say it, but that's relatively straightforward for a DUC IP. I can check on that, but I presumably it is. So,
okay.
I don't know it exactly, but I'll respond directly. But I pretty much believe we have IP that you can configure that's configurable to do wider than 20 megahertz. In particular, there's a lot of 100 megahertz channel bandwidths now that we need to handle.
Next question, is the massive MIMO design available to customers?
I knew we would get that question. Actually, we did it more of a proof of concept and a learning, so it's not really set up as a reference design that we can support with distribution to customers. So the answer to that's no.
What is the maximum bandwidth of the RFSoC that supports 16 transmit, 16 receive antenna configuration?
Okay, so that's a difficult question to answer. There's two answers to it. The first answer to the question is the maximum bandwidth is always limited by your sample frequency. So if you were to, for example, in the ADC sample at 4 gigasample, your Nyquist is 2 gigasample, and I like to use a kind of a rule of thumb of 80% of that. So, maybe about 1.6 of instantaneous bandwidth. It could be sampled and crammed into the programmable logic. The problem is that that's not a realistic scenario. And I think the question is really, okay, if I did a 16 by 16 DFE, how much bandwidth could I get? And that answer is roughly 100 megahertz. So you could implement a 16 by 16, 100 megahertz wide radio with a RFSoC, and that has been done by many customers. But the maximum bandwidth really depends on what you're doing in the programmable logic. But for most use cases, I would say 100 megahertz is the right answer. I can assure you that 200 megahertz won't fit in a single RFSoC on a 16 by 16 configuration.
Another question, where can I get more information on the PCI card for L1 acceleration?
Okay, so what I'd like to do, that's something that we have available, but it's not necessarily gone broadly public at this point. So if you can reach out to your local salesperson, they can probably get more information on it. I would say within the next couple of months, that will be more publicly available on the website. But right now, you'd have to ask your local sales person to get more information on it.
Great. I'd like to thank David for an excellent presentation and Xilinx for sponsoring today's event. You can find out more about their products on their website. Note that this webinar has been recorded, so it will be available to watch within about an hour from now. You can find it in the events section of the Microwave Journal website. If your colleagues would benefit from watching it, please pass along the link. And we thank everybody for joining us today.